Good morning, everyone. I'm Benjamin Liu. I'm from Auckland University. Unlike most people here, I'm not an AI researcher or developer. And I'm here to talk about a legal issue. So you may ask, why do you have to care about the laws and regulations of AI? Well, speaking from experience, I can tell you this. Lawmakers, politicians, regulators, they don't build things. They don't know how to build things. They can certainly make your lives more challenging. So here, this is why we have to care about the law and the regulations of AI. I picked a particular issue, AI discrimination. And today, I'm going to make 3 points. But before that, probably you have seen in the news headlines that AI has this discrimination problem in terms of facial recognition or CV scanning, etc. But is that true? I'm going to say this. First, I believe that the level of AI discrimination has declined over the past, say, 10 years. Secondly, even if AI does have a discrimination problem, it's much easier to fix compared to human discrimination. And lastly, in the past, societies mostly agreed on what is discrimination and what is not. Today, I'm not too sure. First, why do I say that AI discrimination has declined? First, today we have better data set, we have improved algorithms, and also there's a greater awareness among AI developers and researchers in terms of the potential AI discrimination problem. Here is a quote, a very recent quote. It says, "The science from psychology will say, well, those middle-aged white men typically just reflect what they consider normal into AI systems. So when they were creating facial recognition technologies, they considered everyone who was white and looked like them." Is that true? If we look at the report from the US government in 2019, it says, if you check algorithms at the time, yes, the false positive rate for African faces was much higher, 100 times higher, compared to European faces. But that problem has been fixed. Today, the most recent study shows that if you look at the leading algorithms, there's no difference in terms of the AI performance when scanning faces. And also based on our daily experience, when we pass the airport, when we come back from overseas trips, we have to scan our passport to enter into the country. Have you ever encountered a problem of that AI software not functioning well? What about AI screening CVs? Again, the narrative is that AI hiring systems may also enable, reinforce, and amplify discrimination against marginalized groups. But the reality is that if you actually check the data of the hiring practices of firms, there could be a difference among the hiring rate of different groups. But that rate or that difference is not really caused by the software. It's not caused by AI. Rather, it's caused by human decision makers behind the scene. Second claim, AI discrimination is easier to fix. Here are some recent examples of human discrimination. One story is that a female delivery rider bit off a customer's thumb, but she received a suspended jail sentence in the UK. A male jailed for 3 years of punching a police officer. 3 years for punching someone compared to suspended sentence for bit off a customer's thumb. Which one is more serious? Thirdly, in the past, we know what is discrimination and what is not. But today, if you look at the laws and policies, Like in the US, many universities have clear admission policies that favor certain groups but against other groups. And also in the EU, we have the law, or they have the law saying that all directors of listed companies, at least 1/3 of them must come from a certain group or gender. Concluding remarks. Two stories. One is that at one time in the UK, there was an AI researcher giving a public talk. And her question to the audience is that, if we have an AI judge compared to a human judge, which one would you prefer? Most audience members chose the human judge because they believe the human judge has more understanding, whatever. And only one person says, I'm going to choose the AI judge. And that person happens to work in the court systems. I did a similar survey in my class a few years ago. My students are mostly working professionals. So I asked them, if you have to choose between a human AI officer, human resources officer, and AI human resources person, would you prefer the human decision maker or the AI? Again, most of my students chose the human HR, and one student, she chose the AI. And it happens that she used to be a lawyer, and she now works in the human resources department. So I leave you to consider the implications of those stories, and thank you for your time.
Hi everyone, I'm Sharon. I'm a lecturer at Unitec and a researcher in the human domains of AI, and I feel like when Sergio was talking before, I was thinking, I'm right at the end bit where it goes into clinical, and so there's a lot that I could talk about. 5 minutes is just not enough. I don't know how I'm going to do it in that time, but essentially since 2022, we've been simulating and piloting an AI self-rostering technology in high-demand shift workspaces in New Zealand. And last year we ran a 3-month-long pilot. We collected both quantitative data, but also a lot of qualitative data from discussion groups around fit and around well-being improvements, because the technology itself is really driving towards improving staff well-being in high-pressure zones. And so we wanted to see if we could explore that, but we also wanted to look for, the way that users were interacting with the system and the unique elements that related to AI. So for this talk, I've used the consolidated framework for implementation research, which is really just a basic framework that helps you look at all of the potential factors when you're employing a technology into a new setting. So I'll try and do this as quickly as possible. So in this dual site pilot, we had one site that was understaffed, high staff turnover, really quite high demand work, and it was unevenly distributed. So the younger staff were doing a lot more of the high intensity work. They really had a high tension for change. The rosters were being managed across multiple departments. They divided them up so that they could make sure they could actually manage. It was they were really behind the pump, but they had serious compatibility challenges because of their conditions. Whereas at Site B, they were fully staffed, low turnover. They had a relatively lower work demand, and it was more evenly spread. They had really high compatibility with the technology, but lower tension for change, which was predominantly management-led. Site B had a much more mature workforce, and their rostering was previously done by a beloved colleague, which is going to set it up for some really interesting challenges when you're replacing a really important person in a department with a technology. And Site A was comparatively a much younger workforce, particularly our participants, and they had innovation championship right from the top down, and that's actually very rare in Te Whatu Ora, so we were really lucky to see a comparative difference in the sites and get some insight into that. In terms of the implementation process, Site B really wanted to manage that in-house, which wasn't necessarily explicitly stated, but we we can read people, and we figured that out as we went along. The Site A, they really needed all the implementation support that they could get, and everything we offered they took. So we ended up doing a lot more regular small group check-ins. And I mentioned on my first slide that we used a community-based participatory action research approach. It's a really long title for basically saying that we get in and amongst the staff and we try as much as possible to really listen and channel feedback from the ground up and then from up down, and really get the two sides talking. And it's absolutely essential to use an approach like that if you're bringing a technology into a clinical space, because you've got a lot of things, a lot of assumptions on both sides that need to be worked out. Those assumptions are absolutely critical. Okay. So in terms of the thing itself, this is really what Roster Lab were ready to tackle. It's, how flexible did their technology need to be in the space? At Site B, it was pretty straightforward, but Site A required a huge amount of adaptation. And in the end, there were decisions maybe to exclude departments because the rosters were just so incredibly complex and really did stretch the system. I believe at one point, one of the decision-making instances, there was like 3,000 conflicting factors that the AI was deciding on at one point. Okay, so not surprisingly, when we sat down with the sites, this is really just a tiny, small sample of some of the qualitative data that we found. Running out, okay. So really what we were able to show at Site A was that this high attention for change, this real desperate need for something new. They were much more lenient with AI, so we observed the AI leniency effect, which was awesome. For them, they used blaming the AI as a confrontation mitigator, so it really helped them resolve some of the tensions that they had previously had with their roster. Staff had not been able to do anything really prior to that. Those observations were not seen at Site B. So I guess I had two learnings. The first one is that the bigger the problem that the AI is seeking to solve, the more impact it's going to have where the problem is big in the space, which is great, but the more adaptation and flexibility is going to be required at that point. Which leads me to the next one, and that is really that it is absolutely essential to understand the context of the setting and really what you're working with. And I've circled the two, the thing, the innovation, and the implementation process there. And really what I wanted to say was, with Site B, we were more able to focus. I think that they, in the end, really needed a lot more in the implementation process. As a baseline, the tech fit really well in that space. It was pretty uncomplicated. But with Site A, it was the implementation process. We were able to support them through that with the research. But, it was a bit of both, but really it was a huge stretch on the technology. And, my experience from this is that, tech companies, they're ready to go in and adapt their tech. But really thinking about that implementation process and really the social domains and looking for those assumptions and really working through with the staff. Ultimately, it comes down to user uptake. How much will people actually use the technology if they have misconceptions and misunderstandings about it, and also, trust in the output that the technology is producing as well. Yeah. So thank you, guys.
Kia ora everyone, I'm Surangika from Massey University, and in this talk I'll be talking about how we can leverage large language models for low resource languages. First, let's see what low resource languages are. According to Ethnologue, the 7,000 odd languages in the world can be categorized according to vitality, shown in the x-axis, and the number of speakers, shown in the y-axis. As you can see, the vast majority of the languages in the world are either endangered or are being spoken by a small or mid-sized population. This is shown in the blue circles, the outer ones, and if you look at the red inner circles, it shows the coverage of these language classes in different repositories as well as in technology platforms. And if you look at the first row here, it shows the language coverage in different data repositories. And considering that, we can group the language, these 7,000 odd languages in the world, to 6 categories. As you can see, The category 5 is the highest resource category, including English and Chinese, Japanese likewise. Less than 10 languages fall into this category. And the vast majority of the languages in the world are a low resource to extremely low resource and fall into categories 1, 2, and 0. Now we all know the secret ingredient for building good LLMs is high quality data. Now, as we just saw, most of the languages in the world do not have such high quality data. Just to put this into a perspective, if you look at the open source LLMs that are available today, this is the language coverage they have. The highest coverage is in Gemma, that is only 140 languages. And when it says 140 languages, don't get misled because the coverage differs across languages. Languages like English are highly covered and most of the languages will be just barely covered. And even if we have language data for all the 7,000 languages in the world, considering the current technological situation, we won't be able to build an LLM that equally supports all these languages in the world because of this problem called curse of multilinguality. So we are facing intentional or unintentional AI discrimination for these low resource languages because those LLMs don't understand our languages, our cultures, our beliefs, so we are kind of left behind. But if you think of a practical situation, most of us don't need an LLM that supports all the 7,000 languages in the world. All we need is an LLM that supports the languages used in one country or a region, or an LLM that supports languages in a certain family. Considering that, now there is this initiative to build language or region-specific LLMs using a technique called continual pre-training. So using this, we had conducted the research to build an LLM for our language called Sinhala, which is an low-resource language that is only used in Sri Lanka. So as I said, to build LLMs, we need high-quality data. So what we first did was we tried to extract data from existing resources such as MATLAB and Cultura X Corpora, and then we applied some heuristic-based filtering to remove some of the noise in this raw data, and then we went into model training. First, we extracted the vocabulary for Sinhala using this corpus, and using that vocabulary, we trained that Sinhala tokenizer and merged that with the Llama-based tokenizer. And the common practice to extend LLMs for other languages is not to train the model from scratch, but rather to start from a base LLM such as Llama and continually pre-train with the language-specific data. And that is exactly what we did here. We continually pre-trained the Llama to 7B model for Sinhala to produce the Sin-Llama model. And once this base model is there, we fine-tune this for different tasks, and the results were excellent. As you can see, the fine-tuned Sin-Llama beats the base Llama versions by a significant margin. However, when we pre-train or fine-tune these LLMs, the main problem is the computing resources. And most of these low-resource languages are being researched by researchers living in low-income countries, so that's a huge problem. The solution is parameter-efficient fine-tuning techniques such as LoRA, which stands for low-rank adaptation. Because of the initial success of LoRA, there are many different versions of LoRA such as LoRA, Vera, AdaLoRA, PISA, likewise. However, most of these techniques have been experimented or developed for English-related task-specific incremental learning. And when we tried this for cross-lingual transfer, we learned that they are not actually good compared to LoRA. For example, when you tried with Urdu, we see that still the basic LoRA is the best. And even for Swahili, when we tried, although AdaLoRA came as the best, it is just marginally above the basic LoRA. So currently, we are working on implementing a new LoRA technique that can improve the cross-lingual transfer when we do fine-tuning on those LLMs. And next, now we have a pre-trained LLM, fine-tuned for the task, but do these LLMs really capture our culture and value? So we have to check for this alignment and improve these LLMs so that they actually capture us when they do the thinking and reasoning. Thank you.
Kia ora. My name is Dr. Anastasia Mozhaeva. I'm from Eastern Institute of Technology. Today I will be present work AI-driven forensics application for detecting students' mental health risk in New Zealand institution. This work was created by three institutions: Eastern Institute of Technology, UB College of Creative Innovation, and Torrens University, Australia. The project responds to growing students' well-being challenge and counselors' workload pressure by providing a scalable, explainable AI tools, not a replacement for human clinicians. With increasing mental health concerns in tertiary education, early detection and intervention are critical for student success and safety, especially in rural areas. Our research aim is to develop a forensic artificial intelligence framework designed to detect and classify mental health risk levels among tertiary students in Aotearoa, New Zealand. Our approach based on three steps. It's keyword tracking, lexicon-based sentinel scoring, and case-level forensic classification. We create syntaxis data, and our dataset captures a comprehensive spectrum of emotional expressions ranging from extreme negative sentiment to highly positive sentiment. This wide distribution enables nonsense detection of mental health risk indicators across diverse students, narratives, and communication patterns. The granular sentiment analysis forms the foundation for accurate risk classification and early intervention protocols. Here you can see our analytical metrics framework. The framework was designed with human oversight at its core, ensuring counselors retain full decision authority through the triage process. Every classification includes traceable lexical and sentimental contribution, enabling transparent validation of risk assessment. Bias testing confirmed findings across gender and cultural contents, particularly relevant for Maori and Pacific students. Remember that our campuses are based in Tarafiti, where the most students for its Maori students. Here you can see our performance results by data source and our key findings. Its strong negative sentiment correlates with elevated mental health risk indicators, enabling early intervention protocols. The model demonstrates robust performance in distinction between risk levels across diverse students' populations. All risk assessments are traceable to specific lexical features and sentimental patterns, ensuring transparency. Our future work and development. Firstly, we will be working with dataset expansion, expanding the dataset across New Zealand universities and polytechnics to improve generalizability and cultural representation. We also will be working on advanced model. On multimodal integration, we will be integrating multimodal features such as behavioral patterns and academic performance data for comprehensive risk assessment. And I hope we will be working on national dashboard in future. It is our visualization, how our app works. And thank you for your attention.
Yeah, hi, my name is Julian Maclaren. I'm presenting these slides on behalf of Chris Lovell-Smith, who did this work and made the slides, but was unfortunately not able to make it today because he is in Spain. This work's about AI-assisted mussel assessments, and that is mussels in terms of shellfish, not the other type of mussels, the ones that I don't have, but shellfish mussels. I'd like to thank the Victoria University team for their fantastic collaboration over the past few years that has helped funded our work in the aquaculture space. Mang and Bing and the others, thank you very much. Now, so we think New Zealand's aquaculture industry has huge potential. It's a very efficient way and environmentally friendly way to produce protein. Seafood products, they're high value, and we've got a lot of ocean out there, so you can imagine this can be scaled in a way which things like sheep and beef farming cannot. But as we've looked into aquaculture, we've identified a few different ways we think productivity can be improved further. And one of these in mussel farming, it's about the way they harvest mussels. An analogy I like to use is if you have an apple orchard and you want to know when to go out and pick your apples. You might go out and you might look at the apples and you might think, well, should we harvest them this week or should we wait till next week because they'll be riper? But obviously you don't want to wait too long because then you're going to have a lower yield. Some of them will have gone rotten. So it's somewhat similar to mussels. So what they do, they go out on a boat, they look at their mussels, they harvest, they lift some up off the line, they open them, and they look at them and they give them something called a condition score, which is a subjective scoring number between 1 and 10. This mussel apparently has a condition score of 5, but you've got to be an expert to tell that. And then they make harvest decisions based on these condition scores. So, and of course, if you get that wrong, similar to the apple example, it's expensive. It's going to affect your yield. So it would be really good to be able to do this accurately and consistently. So what we've done at Nelson AI through this Harvest Hub startup that we have is we've developed a mobile phone application which lets you take a photo of mussels and gets this condition score. And this is Mark from an industry partner of ours called Maclab in Nelson. He's taking a photo of some mussels which are sitting on our checkerboard. The checkerboard helps the computer vision model get the scale correct and the angle of the phone and things like that. And then it produces a condition score of those mussels. And this is what it looks like in the app. You would click the top here. I think there's an example here. Wait on, here we go. Back to that, let's see. Okay, here's a little demo. So you click mussel harvest analysis. Now you're using the camera, you're taking a photo of the mussels on the checkerboard, and then you're waiting because the image gets sent to the cloud where our data processing is run. And here we go, we've got the condition scores that's color-coded there, along with the length and the width of all those mussels. And then you get to see the kind of average for all of the mussels on the tray and from your data collection process. So, to make this possible, I think I talked last year as well on the same topic, and it was kind of more work in progress at the time because we were collecting data using our research mode in this app. But the data collection is complete. We have 700 mussels have been photographed, and we recorded a lot of other information about those mussels too. Most importantly, the dried weight of the mussel. You can imagine it's quite a lot of effort to take that many mussels and dry them. It's like the cooked dried weight as well. So they're cooked and then they're like freeze dried and then you've got to weigh them. So we have photos of them and we have that ground truth cooked dried weight. And that's what the AI model is trained to predict. So we have this CNN which takes the photo of the mussel and predicts that cooked dried weight. And from that we have a kind of a condition score which is no longer a subjective human condition score but a real prediction of the yield. We've used this and compared it against some human assessments. If you look at this column here, this is consistency, so this is some kind of error metric. If you give the same photo multiple times to different people or to the AI and you look at the difference, you can see that this AI system is more consistent than the human by eye assessment, unsurprisingly. And then if you rank mussels in terms of their expected yield, it turns out we get a better ranking as well using the AI. So now this is actually working. It's out on the farms in the Nelson Tasman region with a few different customers, and we're getting some customer feedback. And as we heard in the first talk this morning, it's all about kind of human factors at this point. How usable is it? How, the various difficulties associated with that we're working through. But overall, it looks like a promising win for AI in aquaculture. Thank you.
Okay, thank you everyone. My name is Mike Watts. I'm presenting this work I'm from the Media Design School in Auckland, and this work was done with Emily Shaw, who's at the Auckland Institute of Studies. She was a master's student doing this work under my supervision. So the idea behind it, or the application area, is, well, bridges. There are a lot of bridges in the world, especially in China, which is where Emily started doing this work. And bridges are made of concrete cracks. If you don't fix the cracks get worse and the bridge falls down. So you need to know if the cracks are there. You need to be able to identify them. And at the moment it's done with, well, this way. They close the bridge, you get this big cherry picker machine, and you hang people over the side and the people stand in the bucket going, yep, that's a crack. So that's slow and inconvenient. Closing bridges is a pain in the neck for everyone, and if you've ever seen the traffic in China, you'd realise it's even worse there. So there's some desire to automate this as much as possible. So that was the main goal of Emily's research, to develop a system that would allow this to be automated, run faster, much more convenient, and hopefully more accurate. And she wanted to do that using the YOLO method, or the YOLO model. So a sort of secondary goal for her was to compare different versions of YOLO. Is newer really better? And if you think newer is always better, then ask the users of ChatGPT. So YOLO came out about, 8-9 years ago. You only look once. Been established pretty much since then as the state-of-the-art of image processing and object detection and object classification. So Emily decided to use that. She sourced a data set. She did have contacts with a company in China that wants to use this technology, but for a start she was using images taken from RoboFlow. So the initial data set, 660 images, but then she stretched it and rotated and resized all the images. We ended up with a data set, a final sort of does this really work data set of 12,000 images, which she split up into the appropriate proportions. And she started playing with YOLO, and what she found out is that it trains really, really fast. So 20 epochs of training, you start to get pretty good performance. By 40 epochs, the performance just isn't increasing. That's for the smaller data set. For the larger data set, she found she only needed to use 100 epochs, and that was quite enough to get really good performance. So if you look at the performance here, percentage accuracies, precision recall, that's pretty good, even for the older versions. Around 90% accuracy, that's actually almost as close as a human would get. Especially if you're standing around in the rain under a bridge. Train pretty quickly, except for the larger data set with 100 epochs, because more epochs, more time. And if we look at the performance over the training epochs, as it trains really fast. There's just no point training it past sort of 100 epochs for the large data set, because it's not going to get any better. So after she tinkered around with the number of epochs and the settings for a little bit, she ran another comparison with a larger 12,000 image data set to more directly compare the different versions of YOLO. And across the board, she found that, yes, later versions are better. And this is average performance over multiple runs, not a single run. So then she took that model, integrated it into RoboFlow. RoboFlow is an image processing data tool set, if you've not come across it before. And it works very nicely. Put an image in, it'll put a box around a crack and say, I'm this % confidence that this is a crack. Now the ultimate goal, of course, is to integrate this into an automated system rather than having fellas hanging off a bridge from a cherry picker. You put a camera on a drone, the drone goes zip, 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 and that's done. And you don't have to close the road or the bridge. So, long and the short of it, YOLO version 12 works better out of the 3 versions that were tested. You do need a fairly big data set. We had to augment this up to 12,000 images. With better resources, of course, and that's something Emily managed to get halfway through her study. She was able to get access to better resources, more GPUs to run this on. And she also found it's also very robust to different lighting conditions. So it works well, but you need a good data set. And Emily has been talking to companies in China about rolling this out, but then she went and got a job somewhere else. As students tend to do. So thank you, everyone. That's my talk.